Hello everyone, this is Vashishta from Aerobee section. Today I'm going to explain about the topic liquid temperature control for a hydraulic turning machine. So coming to the introduction, it is a well-developed concept that temperature variations will introduce dimensional uncertainties in the machining or a measurement process. We consider a machine tool which is designed to have a dimensional length on order of 1 meter and thermal expansion coefficient of a material that is on the order of about 10 P strain. When temperature variation is only 1 mc, the machine tool will experience a dimensional change as large as 10 Newton per liter. This error is probably the maximum a machine designer is willing to allow to the thermal effects for a machine designing to have a surface finish accuracy on the order of 25 Newton meter. Thermal errors are the principal limitations of any ultra precision machines, and a temperature control systems is necessary for this precision level. As we can see in this block diagram of a quite hydraulic precision machine, with the pumping system and actuation system with sensors coming to the oil tank and to the boost pump temperature control system sensor inner loop and outer loop. So the photograph of temperature control system in olden days is given here. That machine is comprised of three major function blocks, which include the temperature control system, the pumping system, and the actuation system. The circulation oil is first pumped by the main boost pump and passes through the temperature control system to remove oil temperature variations. The temperature controlled liquid is then sent to the pumping system to increase oil pressure and flows through the oil pipes about 30 to 40 meter inlet to the machine base for actuation. The exit liquid at the machine base and shower point is then collected back to the tank and resumes the next cycle. The actuation systems and oil tank are installed in the separate room to isolate them from the heat and noise coming from the pumping system. And model construction and estimation. As seen in the photograph of temperature control hardware setup given, a commercially available cross-flow type heat exchanger is used as the main control component to regulate the inner loop liquid outlet temperature due to time varying distributed parameter and long time delay characteristics of a heat exchanger. It is difficult to model. As proposed, the heat exchanger model, which considered the input and output relations with a characteristically, there are four factors that will affect the heat exchanger outlet temperature, which include the inlet oil temperature, the inlet oil flow rate, the inlet water temperature, and the inlet water flow rate. As the inlet oil flow comes from the boost pump, which is a constant displacement hydraulic pump, the oil flow rate can be regarded as a constant with negligible small variations that this factor can be neglected from modeling. The inlet oil comes from the oil tank, which contains about 600 gallons of oil. When the overall system has reached thermal equilibrium condition, then the oil will filter out major temperature and maintain the oil temperature variation order of couple tenths of milli-degrees. As we can see in this model block diagram of liquid temperature control system with the water disturbance model with the heat exchanger plant and outer loop piping and pumping number model. Feed forward controller design. There are two major disturbance as a source come from the environment. One is room temperature variation, and the other is chilled water temperature variation. And here, as you can see in this figure 4, shows the measurement of environment temperature disturbances. The data were taken for 2 consecutive days during April 1996, and this representative to show the variation range of distributions with the time and hour graph with the room temperature and water temperature, measurement of environment temperature disturbances. From the curve shown in figure 4, it is obvious that the room temperature is controlled by an on-off controller because the temperature history during the day shows limit cycle oscillations. The oscillation frequency is estimated at about 2 cycles per hour and the amplitude varies between F250 C. During the night, the laboratory shuts off air conditioning so that the temperature behaves like an exponential decay. The same temperature measurement results repeats on the second day as the room temperature varies between 21 K to C all year long. It will bring dimensional uncertainties to the mission tool. This problem can be solved by using oil shower as the shower oil can block out the effects of room temperature variations and reduce machining errors due to generated heat. The other disturbance source in the water temperature variations, as seen from the curve, the chilled water temperature shown random variations between 5 to 10 degrees, and the maximum water change rate is about 6 meters per second. The variation range is large enough to cause temperature variations of circulation oil. Feed forward control is a very useful method for dealing with the measurable disturbances. Refer to the model shown. The flow shows work. The water temperature disturbances can be compensated by stating following conditions. Design of successive feedback loops. Smith control is the most frequently used method for controlling systems with a excessive long-time delay. It has classically employed a model of the plant characteristic by linear transfer function and a time delay. The Smith predictor uses the model to simulate both the delayed and undelayed state of the plant and uses the delayed state to cancel the real plant output and the undelayed state for feedback control calculations through the block diagram. Here we can see sigma delta Ts and delta referred Ts is equal to CSGB power e power minus STP by 1 plus CSG plus CGS e power minus T minus CQ. According to the model estimation results summarized in table, the liquid temperature control system has faster inner loop dynamics and slower outer loop dynamics. It is necessary to implement at least two control feedback loops so that the faster inner loop can quickly filter out the higher frequencies and larger liquid temperature surges and obtain a liquid flow with quieter temperature variations. Therefore, a uniform temperature environment can be maintained at the shower point. The block diagram of implemented successive feedback loop of a liquid temperature control system is given. Due to different dynamic range of inner and outer loop, a different sampling rate is chosen for each loop. 5 heads is chosen for the inner loop and 1 head for the outer loop. The Smith predictor combined with the PI control has been implemented for both the inner and outer feedback loop. The inner loop includes an additional water temperature feed forward control for disturbance rejection. Care must be taken for inner loop Smith predictor implementation. Due to inclusion of feed forward control, the disturbance effect of chilled water temperature variations can be excluded from the heat exchanger. Outlet oil temperature, so that the outlet oil temperature shows no information of disturbance signal. Therefore, the corresponding control input of inner loop predictor has to be one of which also contains no disturbance information. Otherwise, the predictor will be confused by wrong input and result in worse control results. This is pointed out through a heavier line. It's a block diagram with implementation of successive feedback loops. Water disturbance feedback feed forward, disturbances in mixing plant, varying heat exchanger plant. Temporal mismatch Smith predictor. As mentioned in the previous section, the parameter matches intervention should offer better system performance by institutions since the parameter matches Smith predictor often relates to the transfer the loop controls results, the solid lines are controlled results in the model matched Smith predictor and the dashed lines with the result is considered with the introduction about the vision of Smith predictor that settling the time predictor control system is about 40 seconds faster than the control by the defender. Applying a similar approach to the outer loop, the corresponding results are totally different from the one of the inner loop. The transition response controlled by the model matched Smith predictor becomes unexpectedly sluggish. No matter how hard and tries to become good estimated model, the response is very sluggish and so shows a long settling time. The dotted control history is to be accelerated to the transistence predictor is unable to generate more error signals. Theoretical background. Following Marshall's and his co-workers, assuming SISO system CS is equal to QS plus SS neta by PS plus R theta, where R is equal to e power minus ST PS QS RS are polynomial and finite degrees in S and real constants. The degree of PS is assumed to be strictly greater than other polynomials to simplify the derivations. Experimental test results for temporal mismatch. The comparison between the theoretical and experimental results for both the inner and outer loop. The normalizer KT value of inner loop is 1.05 and the KT value of outer loop is 0.58 due to difference in KT value. No, it's not surprising the system performance behaves differently. The comparison between the inner loop theoretical and experimental results. These are the diagrams of inner loop thermal temporal mismatch results and outer loop mismatch. Coming to the conclusion, the effectiveness of successive feedback loops of the Smith predictor and disturbances feed forward are applied and tested. A satisfactory long duration shower point temperature regulations result in obtained through this approach. We are able to regulate the liquid temperature as at the shower point with a FUM level for frequency distribution less than 0.01 Hz in the presence of large chilled water temperature with 120 seconds. The improvement of system performance by introducing appropriate temporal mismatch is also investigated by theoretical derivations. So this is all my explanation about it. Thank you.